Hey, Math 30-1. We are off on the next journey of exponents and logs. So you have now learned how to see the characteristics of a log of an exponential function. You have graphed it, you have looked at some applications, and you know that you can't solve everything that's an exponential function. You know that, for example, if you try to solve the simple equation 2 to the x equals 7 to the x plus 3, you can't solve that because it's not same base. Anything that is not same base, that it cannot be converted to same, you can't solve. So there has to be something more to be able to solve this. And turns out that the operation of logs, it allows us to solve that. So what is a log? That's what this is, understanding and making sense of it. Turns out it's very closely connected to exponents. So remember the idea of inverses. So y equals f at x equals f at y, or f at minus 1x is the idea of inverse. So if you took the inverse of a function, 2x plus 1, if you interchanged x and y, would become x equals 2y plus 1. If you isolate the y variable, you get y equals x minus 1 over 2. When you have y equals 2 to the x and you inverse it, you get x equals 2 to the y. But how, you ask, could you possibly get x in the y position and y? How do you solve it for y so you can graph it in your graphing calculator explicitly in terms of y? Well, turns out that you need to use logs, that this is the equivalent of that. And that's going to be our journey to understand why is that and that equivalent. Well, how do you convert and graph log functions? Well, graphing a log function is the inverse. But what is a log, we ask? Well, y equals 2 to the x, and when we write our table of values for that, 2 to the minus 1/3 and so on, this should make perfect sense. If I take the inverse, if it really is the inverse of a log, then all I really need to do to graph my log function is just graph the inverse of the exponential graph, which would be x is now 1/8 and so on. Okay, well, if that's true, how do I use my graphing calculator now? Well, it turns out there's this change of base formula that you can use, and what the change of base formula says is that if you have the log of x base 2, most calculators don't have an operation to be able to graph that. So in order to graph the log of x base 2, you can type it in your calculator like this. In other words, the change of base formula says if you have the log of something to this base, you can type it into your calculator by using that change of base formula. So here's what it's really saying. Let's say you wanted to graph. I'm just going to turn the PowerPoint off for a second, and we'll use our graphing calculator if I can find it. So if you notice my graphing calculator, if I wanted to graph y equals 2 to the x, if I want to graph y equals 2 to the x, you guys have done that before. When you graph that, you get a beautiful graph that looks like this, next little exponential graph. But what if you want to graph the log graph? Well, a log graph can be graphed as you look back at the notes. The log graph is log x base 2, so you have to type it in as log x divided by log 2. And when you do that, if we wanted to graph this with technology, we'd graph it, and lo and behold, we get this being our log graph. I wonder why it looks like that. How is it that it looks like that? We need to understand that. So let's go back to our PowerPoint and see. So we now understand where the table of value comes from, that the logarithm function is the inverse of an exponential, so we can just interchange exponential values and we get the log value, right? And we can graph it with our calculator by using this change of base idea. So if you want to type in log, you type in log x divided by log 2, great. But I don't know if we really understand yet what's going on. So how about we look at, now if I look at I'm going to move this up. If I look at our original table of values for y equals 2 to the x, when x equals 1 or 2, or 3, we get these red points. When x is 0, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, and 2 to the 3 is 8. That was our table of values. When we plot the points for our other table of values that we saw before, when we plot those values, we just simply take the inverse of these points and we get this graph, right? Which is the log x base 2 graph. But we still don't understand how these points come about. All we're doing is just taking the inverse, and I guess we're having faith that that's why these points are. All we're really doing when we look back to this chart, we're just graphing these points, and then we interchange and graph the inverse of the point. So, but what is this log? Well, that's what this section we need to go farther. So let's ponder these points. When we type x equals 0 into this thing up here, we get this statement, right? Log x base 2. And if we put a 1 in there, we get log 1 base 2. But what does it mean? How do you get a number out of that? Well, we know what the numbers are. When it's 0, you can't do that. You don't get any point there. It's an asymptote. When you put in a 1, you get 0. When you put in a 2, you get 1. When you put in a 4, x is 4, you get 2 is the output. So what is the machine of logs doing? How are you getting a 3 out of this statement? How do you get a 2 out of this? What does it mean? Well, look over here and see. If we rewrite this statement, how do you really write 0? You could write it with a base of 2, right? So 0 could really be, or sorry, this number right here, when you put in a 1, I'm looking at the wrong one. When you put in a 1 right here, you could really write this 1 as 2 to the 0. And you could really write 2 as 2 to the 1. And you could really write 4 as 2 squared. It's the same base idea that we talked about before. So where does this 3 come from? It comes from this. And where does this 2 come from? It comes from this. And where does this 1 come from? It comes from this. So, wait a second. What are logs? Logs are really exponents. That's what logs are. Logs are exponents that you put on a certain base to get the number you once had. Okay? So I'm going to say that many times as we finish this up. Logs are exponents. That's what they are. And this statement down at the bottom here, the log of b to the m will always be just m, because a log is an exponent. That's what it is. Okay? Well, let's carry on and deepen our understanding. So now we did characteristics of exponential. How do we compare what is an exponential versus log? They're the same functions that have been hit with the inverse stick, right? So that's why I've got the arrows going. The y-intercept is the x-intercept. There is no x-intercept, there is no y. For the characteristics of the exponential, the domain is x is an element of reals. Well, it turns out that that's the range of the other one. And if the range of the exponential is greater than y is greater than 0, the domain is x is greater than 0. There is a horizontal asymptote, there is a vertical asymptote. They are complete inverses of each other, right? The graph of 2 to the x has been reflected in the line y equals x, as you can see up there. Pretty cool, okay? So how do we graph them? How do we do that? Probably the best way is to remember that they're just inverses of they're inverses of the exponential. So if you know what 2 to the x looks like, you also know what its corresponding log graph looks like. It's just the reflection in the line y equals x. As long as you understand inverses, you're fine, right? But for every, right, and I could type it in my calculator, right, log x, log 2 to the x, and I could type it in my calculator like this if I really needed to, but I think we know that if I just reflect it in the line y equals x, or if I, as Mr. K told you before, you could just take x and y and flip it and look up at the lights, and you'd be able to see the blue would become purple, okay? What does the log graph look like of this? Well, if you're pondering, I want you to try and draw it. Well, just reflect a couple of points or flip the paper around, and this point would be here, and this is the point 2 and 1/4, right? So at 2, when x equals 2, you'd have 1/4, so that means you'd have a quarter, and you'd have 2. So that point would now be there. So you're going to have a graph that looks like this, right? I don't need the calculator to tell me that. It's simply the inverse of the other graph, right? I take the inverse. Now my graph is a little bit off because I was just doing it rough, but that's what it would be, okay? What about 3 to the x? What's the corresponding graph of 3 to the x? Well, graph y equals 3 to the x by hand. At 0, it's 1. At 1, it's 3. At 2, it's 9. I plot those points. What does the blue one look like? Well, reflect those points across the line y equals x. Take the inverse, and you'd get these blue ones. So logs are the inverse of, in terms of the graph, are the inverse of exponential graphs. So as long as we understand the exponential ones well, we can just flip things around to find our others. So what are the characteristics? Reminding us, looking very similar to what we did, to what we did in exponential graphs, right? Ponder, write, reflect, and please ask questions tomorrow if these characteristics are just things that we wrote down but don't really get, okay? All right. Don't need to memorize this. You just need to be intimate with the exponential graph, the growth or the decay, and these are just the reciprocals of, the inverses of those, okay? How do we convert from expression? So now we're getting deeper, and that was just the graphs. Now we're going to look more specifically at, well, what are we looking for when we want to convert back and forth in logs? How do they actually work? Well, multiplication is a shortcut for addition, right? 4 plus 4 plus 4 is really 7 4s. And if I had a lot of 4s being multiplied together, it'd be easier just to write 4 to the 7. Well, logs are really a short way of writing exponents. Logs are exponents, right? The log of 25 base 5 is 2. How come? Because you need to understand this. Here's the notation. 10 squared equals 100. 10 raised to an exponent of 2 gives you 100. That's the base, that's the exponent, or we might even say logarithm, and the result is 100. The exponent to which 10 must be raised to give 100 is 2. The other way of saying it is the logarithm to the base 10 of 100 is 2. Logs are exponents. The exponent that you put to a base of 10 to give you 100 is 2, okay? That's why the log of 100 base 10 is, base 10 is 2. All right? So now, let's ponder. Again, there are two different ways of writing the same statement. So when we convert, when you see something like this, these are actually equivalent statements, okay? They're saying the same thing. One is saying it in an exponential way, one is saying it in a log way, okay? These two statements over here are not the same. They're just different forms. So when you watch this little video, there's a difference between form and a difference between the a difference between the form and the actual function. And we need to discuss that maybe further tomorrow. What I'm saying right here is this. The form that it is in, and we'll see it more, this and this right here are exponential, an exponential statement and a logarithmic statement, but they are actually the same thing, just written with different lipstick. You've dressed it up in an exponential way here and a logarithmic way here. However, um, in different situations, it's not the same. So in this case right here, this, although it looks exponential, is actually a log function with exponential lipstick on. It looks exponential, but it's really a log function because it has y in the exponent, and the only way to get out is to write it this way. All right? This is a log function, but it's written in log form. When I look up here, this right there is an exponential function, and it's also, I'm going to put in brackets, exponential form. Okay, so it's a picky little thing, and we'll talk about more tomorrow, but I could rewrite this like this. And then I didn't take the inverse, I just wrote this. Log y base b equals x. And you might say, well, that's silly. No, this is now an exponential function still. I didn't change the function at all, but it's now written in log form. It's the exact same thing. So this is something we need to really make clear tomorrow, and I'll leave it till then. I just wanted to express it right now, okay? So now we just need to be clear about how these things work. So how do you write 2 to the 3 with logarithmic lipstick? Well, you simply say, oh, log of 8 base 2 is 3. 2 to what exponent is 8? 3 to the 4 is 81. Well, that just means the log of 81 base 3 is 4. 5 squared is 25. I'm converting it to the opposite form, right? So 5 squared is 25. A logarithm tells the exponent to which the base must be given, right? If you see anything that doesn't have a base, it's considered base 10. That's the other thing we need to be clear of. So now you've got some work to do. I want you to go through this chart and convert these and evaluate these. So I'll do the first one with you, and then you carry on. Okay, so the first one, a fancy way to say that is log 1,000 equals 3. I want you to do the rest. Make sure you pause and then come back and look, okay? All right, I'm going to squeeze down so you can see the rest. Ooh, that must mean 12 to the 0 is 1. Oh, how do I write that as a log? Well, the log of p base q is 2. So again, in all these questions, what's the base, what's the exponent, what's the number? So clearly, when you look at this, you don't hesitate. That's the exponent, that's the base, this is the number. So a log statement means the same. You're obviously taking the log of 2 to a base of x, and that would give you y. The exponent that you put on x to give you 2 is y. The log of r base p is q, and so on. Okay? Base, exponent, number. All right? Converting the exponential form when there's more than one step. Okay, well, if I had m log n base bq, well, sometimes you got to move stuff around so that you can convert it to exponential form. So you got to get rid of these coefficients. So now you say, oh, just get the log by itself. Now that I've got the log by itself, oh, this is the base. Oops, I'm in a different color. This is the base, this is the exponent, this is the number. So I don't think you have any trouble saying, oh, that's easy. I take a base of b, I put it with q over m, and that's supposed to equal n, right? And that's how it goes, okay? And so same thing here. I got to move that 2, isolate the log, and now I can go b to the 9 over 2 equals 5. I need to get rid of this so you can see, oh, I got a negative there. I got to get rid of that negative. Move the negative over. 5 to the minus n equals m. And lastly, move that 3. Now I've got 1/2 divided by a negative 3. Whoa, what's that going to be? Seems like a minus 1/6. And I got 2 to the minus 1/6 equals r. Changing the lipstick of this statement, right? We're dressing up different, okay? There is all kinds of cool conversions that happen. We're not going to talk about that. This is going to be part 2, but I did want to show you, man, we got pH, we got decibels, We got all sorts of things that follow logarithmic conversions, and we're not going to try and fully understand that right now, but it is important, okay? So what do I do if somebody wants to evaluate what's the log of 25? I think we get the idea. For some of you, you can just say, oh, to what exponent do I put on 5 to get me 25? So in other words, if you're looking for it, you could say, well, let's just put an x out there, I don't know, and change it to an exponential statement like this, and now evaluate it, okay? Obviously, 5 must be raised to a power of 2 to get you 25, so it ends up being equal to 2. And personally, I tend to think more like the blue than I do the black. So when I see this question, I think this, 5 to what gives me 25? Well, that's easy. 5, because 25 is 5 squared, if you think back to our same base stuff, obviously x equals 2. Okay, so there's a couple ways you could kind of look at it. So we know that the log of 27 base 3 is 3. We know that the log of 32 base 2 is 5, using that same base. We know that the log of 125 base 5 is 3, and the log of 100 base 10 is 2. What about the log of 1? What's that? What's that? Well, the only way you can get 1 is to put 0 on any base, so that's just going to be 0. What about the log of b to the m? Well, that's just simply going to be m. What about the log of 0? What is that equal to? Well, the blue shows you what we want to try and be thinking right there. The blue shows you that, well, if you don't know, the equivalent statement for this is b to the x equals 0. What exponent do you put on any base to give you 0? And the answer is, you can't. That's not possible. What about the log of negative 4? What exponent do you put on 2 to get you negative 4? That's going to be awfully tough. No, you can't do that either. And lastly, what's the log of x base 2? Well, you need to make sure that your numbers are greater than 0. So you cannot take log of anything that is smaller or equal to 0, okay? And in this question, I'm going to pause and just start. So as we handle this puzzle, a good diploma exam type question, we say to ourselves, I remember this, we did a little bit of this, so I need to solve this and rewrite this in exponential form. So I need to get the log by itself. So log n base p is equal to, well, the first thing I should do is go q minus 5, and then I also have to divide by m. So I'm going to end up with the log of n base p. I took the 5 over and then I divided by m, and I end up with that. So now I can say, okay, well that means that p to the q minus 5 over m is equal to n. And that's now an exponential form. But when you look over there, you say to yourself, what, I don't have any of that stuff. In fact, if you look, they don't have any m's here. So none of them, they're all q minus 5. So how do I rewrite mine? Well, I need to do a little bit of magic because right now I'm scared and sad. So what I say to myself is, well, wait a second, I just need to get rid of this m right here. So they're being a little tricky. So I say, well, I can use my exponent skills and do this. I can take my answer that I have there, n equals p to the q minus 5 over m, and I can just multiply or take this all to an exponent of m. And when I do that, the m's blow up because you can put the m in there, and you're left with now an answer of p to the q minus 5 equals n to the m, and the answer is clearly going to be B. Yay, B. Okay, we look at the next question. The value of this log is, and we evaluate each of those. What's the log of 625 base 5? Turns out that that is 4. What's 3 log 47? Well, that's 3 times 2. What's the log of 1 over 16? Well, that would be 2 to the minus 4, right? So what's the log of that? That's minus 4. What's the log of b base b? The only way that can happen is 1. And what's the log of 1 to any base? That's 0. If we add all this up, we end up with 4 plus 6 minus 4 plus 1, which equals 7. Okay? And lastly, we were supposed to rank these logarithms. Well, we could use that change of base that we had in our calculator. Whoopsie, we don't want that. We could use the change of base in our calculator, but instead we're going to do something where we're just going to use some common sense. If I kind of use benchmarks, I guess, this is going to be not quite 3. 4 to the 3 would be 64. So, whoopsie, we want to postpone that. So this is going to be, I don't know, I'm kind of making up, but this is somewhere around 2.8. The log of 36 base 6, well, that's exactly 2. The log of 10 base 3, that's really just past. 3 squared is 9, so this might be, I'm just guessing, but 2.1 something. And the log of 5 to the 20, well, that's not even 2. So this would be, I don't know, I'm going to guess it's somewhere around 1.7. So even though I don't know how to exactly find it, I know roughly what it is. So clearly, this would be the smallest. This is going to be the next smallest. This is a little over 2, so that's the third. And this would be the biggest one, okay? And that's just using some common sense. And now there's just some information that I wouldn't mind you reading. So you guys, we will see you tomorrow in class.